Relative lowering of vapor pressure. Firstly, let me teach you some key concepts like colligative properties. I always teach these three important points about colligative properties. Colligative properties are physical properties of a solution. Secondly, it depends on the number of solute particles in a solution. Thirdly, colligative properties do not depend on type or nature of solute particles. For example, consider these three objects containing equal amount of water. We know that the boiling point of water is 100 degrees centigrade at sea level. Now I add 5 mole of salt to the water to form a solution. We observe that the boiling point of this solution is 105 degrees centigrade. On the other hand, I add 10 mole of salt to the water to form a solution. We observe that the boiling point of this solution is 110 degrees centigrade. Thus we say that as we increase the solute particle in a solution, boiling point of solution increases. Let me repeat it. As we increase the solute particles in a solution, boiling point of solution increases. Therefore, we say that boiling point is a colligative property because it depends on the number of solute particles. Hence, note it down this important concept. Here, let me explain one important point which I always ask. What is meant by colligative properties do not depend on nature of solute particles? Well, consider these two objects containing equal amount of water. Now I add 5 moles sodium chloride to it to form a solution. When we observe its boiling point, it is 105 degrees centigrade. Secondly, I add 5 mole potassium bromide to it to form a solution. When we observe its boiling point, it is 105 degrees centigrade. We know that the salt sodium chloride has two types of ions, sodium ions and chlorine ions, while the potassium bromide has also two types of ions, potassium ions and bromine ions. Thus, colligative properties do not depend on the nature of ions. I mean, either it is sodium ion or potassium ion, but it depends on the number of ions. Here, both the objects contain same type of ions. Hence, their boiling point increases by the same amount. Thus, note it down these basic concepts. Remember that there are 4 colligative properties like relative lowering of vapor pressure. The second one is elevation of boiling point. The third one is depression of freezing point. The fourth one is osmotic pressure. Remember that in this lecture, I will only teach you the relative lowering of vapor pressure, and we will discuss the 3 remaining properties in upcoming lectures. Here, let me ask you an important question. Is vapor pressure a colligative property? The answer is no. Vapor pressure is not a colligative property. It is relative lowering of vapor pressure which is a colligative property. So note down these important points. Now to learn relative lowering of vapor pressure, we have to learn some key concepts like pure vapor pressure P0. Remember that examples of volatile liquids are water, acetone, mercury, gasoline, etc. Now consider water in this closed container. I represent water by A. We know that vapor pressure of water is built in this closed container. We write vapor pressure of pure water is equal to PA0. Let me repeat it. Vapor pressure of pure water is equal to PA0. Hence P0 means vapor pressure of pure liquid or vapor pressure of only one liquid. Thus note it down this fundamental concept. Now we will learn partial vapor pressure in a solution. Remember that the examples of non-volatile solutes are glucose, sucrose, urea, etc. Now I take water in this container. We represent it by A. Secondly, I take glucose in this container. Let I represent it by B. Here, let me ask you, What is the pure vapor pressure of water in this container? Well, we already learned that the vapor pressure of pure water is equal to PA naught. Secondly, the vapor pressure of pure glucose is equal to PB naught. Glucose is a non-volatile solute, hence it exerts no vapor pressure. So PB naught is equal to 0. Now I combine water and glucose to form a solution. In this solution, there are two types of particles, water particles A and glucose particles B. Water is a volatile liquid, hence its vapor pressure is built in this solution. Remember that we represent partial vapor pressure of water in a solution by PA. Let me repeat it. We represent partial vapor pressure of water in a solution by PA. Similarly, we represent partial vapor pressure of glucose in the solution by PB. It is a non-volatile solute, hence partial vapor pressure of glucose is 0. Thus we learned two very important concepts. One is PA naught and the another is PA. PA naught is the vapor pressure of pure liquid, while PA is the partial vapor pressure of a liquid in a solution. Hence noted down these two important points. Now I will teach you two important concepts which no one is teaching. What is meant by lowering of vapor pressure and relative lowering of vapor pressure? Well, consider water in this container. Let its pure vapor pressure PA naught is equal to 80 atmosphere. Now I add some glucose to it to form a solution. Let the partial vapor pressure of water in this solution PA is equal to 60 atmosphere. We can see that the vapor pressure of the water decreases from 80 atmospheric to 60 atmospheric. This is known as lowering of vapor pressure. So whenever I ask you to explain lowering of vapor pressure, you should always answer this question like this. The decrease in vapor pressure of pure water or liquid when we add a non-volatile solute to it is known as lowering of vapor pressure. I mean, lowering of vapor pressure is equal to PA naught minus PA. The value of PA naught is 80 atmosphere and that of PA is 60 atmosphere. I get 20 atmosphere. Hence, the lowering of vapor pressure is 20 atmosphere in this case. Remember that the formula of lowering of vapor pressure is PA naught minus PA. On the other hand, relative means comparing two values. In relative lowering of vapor pressure, we compare lowering of vapor pressure to pure vapor pressure. We know that the formula of lowering of vapor pressure is PA naught minus PA, and we represent the vapor pressure of pure liquid by PA naught. We know that the value of lowering of vapor pressure is 20 atmosphere and the value of vapor pressure of pure liquid is 80 atmosphere. I get 0.25 atmosphere. Thus remember that the lowering of vapor pressure is equal to PA naught minus PA, and the relative lowering of vapor pressure is equal to PA naught minus PA upon PA naught. Hence note down these two important terms because I will play too often with these two terms. Now we will derive the formula of relative lowering of vapor pressure. Consider closed containers. Let this container contains pure water. Its vapor pressure is PA naught. Let this container contain a non-volatile solute like glucose. Let its vapor pressure is PB naught and it is equal to 0 because here the solute is non-volatile. Now I combine them to form a solution. The partial vapor pressure of water A is PA in the solution. The partial vapor pressure of glucose B is PB in the solution and it is equal to 0 because it is non-volatile. Now according to Raoult's law, partial vapor pressure of water PA is directly proportional to its mole fraction. It means that if we increase the mole fraction of water in the solution, its partial vapor pressure increases. Here, to eliminate the sign of proportionality, we have to put some sort of constant. I write PA is equal to K into its mole fraction. In the previous lecture of Raoult's law, we learned that K is equal to PA naught. If you have missed our previous lecture on Raoult's law, watch it and its link is given in the description. Hence, I put the value of K in this equation. I get partial vapor pressure of water A in this solution is PA is equal to PA naught into its mole fraction. Let this is equation number 1. Here, we are interested to find the relative lowering of vapor pressure. We know that mole fraction of water A plus mole fraction of water B is always equal to 1 in the solution. I shift mole fraction of glucose B from left hand side to right hand side. I get mole fraction of water is equal to 1 minus mole fraction of glucose. Let this is equation number 2. Now I will plug in equation number 2 and equation number 1. I get partial vapor pressure of water is PA is equal to PA naught, and instead of mole fraction of water, I put this value 1 minus mole fraction of glucose. Now I open this bracket. I get PA is equal to PA naught minus PA naught into mole fraction of glucose. I shift PA from the left hand side and I shift the term PA naught mole fraction of glucose from the right hand side. I get PA naught mole fraction of glucose is equal to PA naught minus PA. We already know that the term PA naught minus P is lowering of vapor pressure. Now to find the relative lowering of vapor pressure, we will shift this PA naught to the right hand side. We get PA naught minus PA upon PA naught is equal to mole fraction of glucose. Hence this is the relative lowering of vapor pressure and it is equal to mole fraction of glucose or mole fraction of the non-volatile solute. Secondly, we know that mole fraction of glucose is equal to number of moles of glucose upon number of moles of glucose plus number of moles of water is equal to PA naught minus PA upon PA naught. This is another way to write relative lowering of vapor pressure. Remember that in case of dilute solution, the number of moles of solute B is very small and the number of moles of solvent is very high. Hence we neglect the number of moles of solute and the denominator and we get this equation. Thus note down all these important points about relative lowering of vapor pressure. Now I will teach you some important numerical problems of relative lowering of vapor pressure. Consider this numerical problem. The vapor pressure of pure water is 80 mmHg at 30 degrees centigrade. Find the vapor pressure of a solution when 90 gram of glucose is dissolved and 36 gram of water. Firstly, I write the given data. Remember that here the solvent is water and I represent it by A, while glucose is a solute and I represent it by B. The given vapor pressure of pure water is PA naught, which is 80 mmHg. The given mass of glucose is 90 gram. The given mass of water is 36 gram. We know that the molar mass of glucose is 180 gram per mole and the molar mass of water is 18 gram per mole. Now I will find the number of moles. The number of moles of water Na is equal to given mass, which is 36 gram, upon molar mass, which is 18 gram. After calculation, I get 2 mole. Secondly, the number of moles of glucose is Nb, which is equal to 90 gram upon molar mass, and that is 180 gram per mole. After calculation, I get 0.5 mole. Now here I teach very important trick. Remember that whenever you get a numerical problem in which you are asked to find partial vapor pressure of a solution, you can use these two formulas. According to Raoult's law, partial vapor pressure of a solution Pa is equal to Pa naught into its mole fraction. And according to relative lowering of vapor pressure, mole fraction of solute is equal to Pa naught minus Pa upon Pa naught. We can see that partial vapor pressure of a water in a solution is Pa here and Pa there. Remember that we will never use this formula because it is too lengthy. Rather, we will use the Raoult's law in order to get quick answer. Here, I put the values in Raoult's law. Vapor pressure of pure water is 80 mmHg, but we need to find the mole fraction of water which is unknown. Mole fraction of water XA is equal to Na upon Na plus Nb. Mole fraction of water is equal to the number of moles of water which is 2 mole upon the number of moles of glucose which is 0.5 mole. Now I plug in these values in this equation. I get 0.8. Now I will put the value of vapor pressure of pure water which is 80 mmHg in this equation. And I put mole fraction of water which is 0.8. After calculation, I get 64 mmHg. Thus the partial vapor pressure of water in this solution is 64 mmHg. Hence note it down. Finally, let me teach you one important numerical problem from JEE main exam of 2015. The vapor pressure of acetone at 20 degrees centigrade is 185 torr. When 1.2 gram of a non-volatile substance was dissolved in 100 gram of acetone, its vapor pressure was 183 torr. Find the molar mass of the substance. Well, I write the given data. Here, the solvent is acetone and I represent it by A, while the solute is unknown and I represent it by B. The given pure vapor pressure of acetone is Pa naught is equal to 185 torr. The given mass of unknown solute is equal to 1.2 gram. And remember this given mass of the unknown solute which I will use. The given mass of acetone is 100 gram. The partial vapor pressure of acetone in solution Pa is equal to 183 torr. Remember that the molar mass of acetone is 58 gram per mole. The required value is molar mass of unknown solute. Let it is U. Now I will find the number of moles. The number of moles of acetone is equal to given mass which is 100 gram upon molar mass which is 58 gram per mole. I get 1.73 mole. Remember that I round off every value to 2 decimal places. Otherwise, you will get another answer. We know that mole fraction of unknown solute Xb is equal to Pa naught minus Pa upon Pa naught. Our mole fraction of unknown solute is number of moles of solute upon number of moles of acetone is equal to Pa naught minus Pa upon Pa naught. Now I will put the given values in this equation. The number of moles of unknown solute upon the number of moles of acetone, which is 1.73 mole, is equal to the vapor pressure of pure acetone, which is 185 torr, minus the partial vapor pressure of acetone in solution, which is 183 torr, upon pure vapor pressure of acetone, which is 185 torr. After calculation, I get 0.019 moles. Now we will find the molar mass of unknown solute. We know that the number of moles of unknown solute Nb is equal to given mass, which is 1.2 gram, upon molar mass, which is unknown, and we represent it by U. Secondly, we calculated the value of number of moles of unknown solute, which is 0.019 moles. I write 0.019 moles is equal to 1.2 gram upon U. After calculation, I get U is equal to 63.15 gram. Around about, the molar mass of the substance is 64 gram. Thus noted down this important numerical problem. I hope that you have learned all about relative lowering of vapor pressure.